discussing is a Python program that I've released on the Black Hat website. So if you go click on the Black Hat website under the schedule, you'll actually see a GPL, so I guess half of you can't click, but you know, for $40,000, I'll BSD license it to you. It's a GPL program that takes bytes and changes them into other bytes, like most programs. But we'll be discussing in detail what it does, and you can read through with it if you like, or read ahead of time, or comment on my poor coding style, whatever strikes your fancy. So I think I might as well start. Seems like there's a lot of people here, and it's about time to start. All right, so this presentation was originally written because I thought there was a lot of process involved in understanding what an exploit really is that I thought the traditional "this is a buffer overflow" talks were missing. And so I wanted to get a bit into detail on the process. And to do this, I analyzed an existing vulnerability, although this could apply to any vulnerability that you're going through. I want people to understand the mindset. I'm the founder of Immunity Incorporated. It's a New York City-based company. It does consulting and products. One of the products you just sort of saw, it's Canvas. It's kind of a toolkit for demonstrating exploits, or if you're someone who writes exploits, it's a toolkit for writing exploits and demonstrating exploits. I also sell a Solaris kernel forensics tool, which will detect kernel Trojans. It does this fairly well. I also give away Spike and Spike Proxy. Spike Proxy is just as good as any of the web application assessors that you've seen and used, perhaps in your company, except free and open source. And Spike is a kind of groundbreaking tool for finding vulnerabilities like the one that I just showed you. And I have a whole nother Black Hat talk on that. Hopefully you caught that. I found vulnerabilities in many programs, and some of these have gone public and some of them have not. And I guess you can do a bug track search on me to find out exactly what I have done that is public. This talk specifically does not cover everything that you need to know to write a Windows overflow. No one talk could do that. But many talks, I think, leave out important things or gloss over them or haven't touched them. Some of these things are heap overflows. This talk is not going to be about a heap overflow. But there's a lot of interesting places to go when exploiting a Windows heap overflow that I don't think any talk or paper has really done. Fixing the heap after overflow occurs is probably the main one. The other one is actually finding the function pointers as you trace through the exception handlers and doing the multiple overwrites. There's actually a New Zealander who was keying me into ways of doing multiple overwrites recently. The PE header parsing, I think, has been covered fairly well now by several people. If you went to Riley Hassel's talk, he discussed it a bit. LSD has come out with their paper and shellcode stuff on it. In reality, it's been known for quite a while. Library call redirection is something that I think under the Windows platform is much more valuable than under the Unix platform, where it's known as syscall redirection. And I'm not going to be discussing why, but Canvas is built, or the Windows part of Canvas is built on that. The other sort of Windows specifics for exploitation or writing an exploit, tokens and impersonation and that entire morass. Probably one of the bigger design mistakes in NT was putting multiple authentication or multiple sort of authorization mechanisms together that will encapsulate in one process different user levels, which is probably not wise. DCERPC is poorly understood by anybody. I think it's just too complex to understand. And so exploiting the holes in that. And I think also the Unicode is something that, unlike in Unix, in NT is kind of a base of the OS. The internal function calls use Unicode entirely. And so actually dealing with Unicode is another thing that most people haven't had to do, or if they have done, have found some tricky way of getting around it. A lot of this presentation is not needing a tricky way to get around it. OK, so if you look at like what a Unicode exploit is typically described as if someone releases an advisory and they say, I have a Unicode exploit in following product. This is what they really should be saying. What they really mean is I found some way to get arbitrary data into Unicode form. But in reality, a true Unicode exploit, and this is going to be very common as you find exploits in DCOM, is that you'll get some sort of thing, IS in this case, any process taking in an ASCII string. It's going to take a native string in, and it's going to say, OK, now that I have it, I need to give it to somebody else. And it's going to send it across with an RPC call to some other process, or even itself. And when it does that, it'll probably pre-convert it to some version of Unicode in whatever localization that it thinks it wants to put it in. And that other process, which could be an entirely separate memory area, it's an entirely different process, is going to overflow. And now you're in a situation where you've overflowed and the data you have is in Unicode format. And so it's sort of a special case of the filter sort of aspect of exploitation. There's a filter put onto your input string that is restricting what you can do during your exploit. So I kind of strictly defined it as a Unicode exploit does not allow you to access your shellcode as non-Unicode. In the case of, for example, the locator exploit, it's actually a Unicode string, but you can put arbitrary binary data into it. So you're not really restricted in any way. But in the exploit that I chose to do this demonstration on, you are. And I think it's much more, it's a restrictive case. And if you can show that the restrictive case is easy and doable, then you can expand that to the other cases. So it's really, I found it very unreliable trying to find a way to get arbitrary binary data into this particular exploit that we're going to be talking about. And we'll talk about kind of what sort of string manipulation is done by the process as we go through. So the one we're talking about today is a known vulnerability in Microsoft Content Server 2001. It's been known for a while. It's remotely exploitable via just a simple post to a login page that it installs during the installation process. And Microsoft Content Server, I've never actually used it, but it does connect to SQL Server and it manages your content, I assume. But it's a Stack Overflow and it's Unicode, and that's really all you have to know in the beginning. So it was announced August 7th, credited to this guy. I can't pronounce his name correctly, I'm sure, so feel free to read it. But there were actually two other remotes that he found in Microsoft Content Server. In 2001, I think the 2001 server line, I'm sure, was not nearly as robust as the stuff coming out now. But in this case, he found a couple other things, and I haven't even looked at those things since I thought this problem was more interesting. But those things as well are just the same remote roots. So if you read the advisory, you'll get some useful data out of it. You'll learn that a buffer overflow somewhere in a low-level function that performs user identification is accessible via some web page functionality of some kind, right? So taking it to its fuzziest, that's all you know about the vulnerability when you're going to look for it. And the mitigating factors listed are, it's not there unless you install it, but also URL scan, which is a Microsoft tool to limit the length of URL and URL arguments, would block any URL with non-ASCII data. And one thing I found odd about this was that the actual overflow is not in the URL as far as I can tell. Maybe there's some other overflow that I haven't been able to find in the URL. And that's often the case, actually, is that when you find one overflow, the whole code is riddled with problems. But in this case, I didn't find an overflow in the URL. And I did look for a while. I wasted a couple hours looking for one. And it also says that the attacker would need to construct valid executable code using only ASCII data, which makes it sound incredibly difficult. So those of you who've downloaded my Python script from the web page can now construct ASCII-only executable code in Unicode format. But we're going to be talking kind of how you can do that. So to find the process of finding a vulnerability is what finding and exploiting it successfully is kind of what I wanted to walk through. Basically obtaining the software and installing it. And then I just said, what process is running as local system, because the advisory said you could get system, and is new. And the one that sticks out is something called AE Security Service. So you attach to it with OllyDebug, which is the best debugger that I've found for doing this sort of thing, although you may disagree with me with that, depending on. It's called OllyDebug. Ollie. His name is Ollie. He wrote a debugger. He called it OllyDebug. That's good. So you can Google that. It'll pop up. It's free, but it's not open source. But it's good. It's got a nice GUI. That's what you saw earlier, if you were here. Anyway, so I have this program called Spike Proxy, which takes small strings and makes them bigger in the context of a web application. It does that fairly well. You click overflow after browsing around on the content server pages, which you can see via the IIS MMC plugin. And you wait, and OllyDebug breaks, and that's where the overflow is. And the bolded part, I bolded. If you can see it, it's the actual machine name. That's the first overflow that you find. This is just some random login page. And you have to make sure that you actually add your overflow string to the end of that. And you can't interrupt that winnt : //, which is what you're really seeing there. So the overflow is interesting because a lot of tools will just replace the winnt : // string with their own long string. And that actually won't find the vulnerability. You do have to sort of have a certain format to it. And I got lucky that Spike Proxy does just append things as well as prepending them and replacing them. So that's the vulnerability. And long string out of small string. That's what most vulnerabilities are. If you just quickly do in OllyDebug, all these little windows that you see here are just me screen scraping from OllyDebug. So if you screen scrape OllyDebug after finding that vulnerability, and you look at the call stack little functionality, they'll show you this little thing, which shows you clearly that the string I sent was 40,000 bytes long, and they appear to be using that value as the maximum length. So the source, which is what they really should have been using, or actually some calculation based on the source, is much smaller than 40,000, it turns out. And so it crashed, and the call stack was set this way. So this is kind of like, what am I dealing with? You're dealing with WCSN copy, which you can tell right away is going to be a Unicode operation because of the W. And look at the fact that you control the source and the dest is on the stack, which if you are looking at the registers, you can tell which is ESP, so you know where the stack is. So just to briefly revisit what a typical Win32 buffer overflow looks like, you basically trash the whole stack. And somewhere on the stack is going to be a little function pointer called an exception handler. And you're going to overwrite the exception handler. And after the exception happens, because you're going to overwrite the segment boundary at the end of the stack, it's going to give you control, and you're going to direct it to some other thing that says call ESI or call some other register. And in this case, if you look at the screen, you'll see that ESI has a pointer to our string, which is going to then execute our string if we can call ESI. So that's the typical process of obtaining control and executing your shellcode. And once you've done that, you've pretty much won the game in most cases. So unfortunately, this particular Microsoft Content Server overflow is not a typical overflow. It has a lot of wrinkles to it, which is why I found it interesting enough to write a presentation about it. But just to give you some context, from beginning to end, from reading the advisory and saying, this one might be interesting to look at, to finishing the exploit took about 2 weeks, because there was a lot of infrastructure that had to be done to do the exploit. But just that's where we're going. We're going to have a working exploit at the end, in case you're wondering what the magic ending was. But the real issue with this is that there's no standard way that I can find to get your binary data into that string that actually does the overflow without having it be unicoded. And unicoding is different on Service Pack 2 and Service Pack 3 in the terms of this, or at least as demonstrated by this overflow. The unicoding process can change a little bit, which makes your exploit a little bit variable. But The main difficulty is that if you're just restricted on that filter and you're thrown through that function, there's a huge subset of the normal operations that you would do. There's a huge set of this stuff that you can no longer just easily do. So a lot of this presentation is going to be a little bit split between the Service Pack 2 situation and the Service Pack 3 situation. But if you think about the Service Pack 2 situation, which is more restrictive, you're in a better state for the Service Pack 3 situation, because it only took like a day to sort of, or a few minutes really, to port over the Service Pack 2 to the Service Pack 3. But the Service Pack 2 is so restrictive that it really took a lot of effort. Okay, so cataloging the situation when the overflow happens. You get EIP, you have it, and it's pointing to a version of your string, right? You can say that EIP I own and EBX points at me, and that's a good situation to be in. You can say that I know that there's another version of my string on the heap somewhere, and it's important to sort of, as you write an exploit like this, catalog what you control in all of memory and in the registers and in any other state that you can control, instead of just looking at what's on the stack or what's on the particular string that you've overflown. And you have to look at kind of the filter that's been applied. It's basically just a function. The Unicode function that got applied under version SP2 actually differed between the version that was on the stack, which was a very restrictive UTF-16 something. There's a few different versions of Unicode that get applied apparently. But you just look at what it is, and it's very strict in what it allows on the stack. And if you looked at the one on the heap, it wasn't as strict. So you maintain kind of a little notepad list of, at this address, I have the following restrictions on my string, and it got transformed in the following way. And at this address, I have the other restrictions. So you have kind of a little table of what kind of resources you have available to you. And because EIP is on the stack in this case, it was subject to the most restrictive case in that you couldn't have anything above 7F. And the other major issue is that you're not in inetinfo. You don't have a raw socket you can just grab. So as you're writing an exploit, you always think about, how is this exploit going to communicate with me, the attacker? And in the case of a lot of programs, it's just going to try to steal that WinSock socket. But in the case of something that's in a DCOM thing, you don't even know what machine it's on. So having it communicate over the same socket is not an option. So the constraints that you view are, with a Unicode, are very often this sort of thing. You're going to get the choice to overwrite EIP with a certain set of numbers. And this is going to correspond to a certain set of memory addresses that you can jump to. So I just described it as sort of a Ford-like function. You can have any kind of car as long as it's black. Or in the case of this, you can have any kind of EIP as long as it's in this following format, which is you can't have zeros because zeros will terminate your string. You can't have A, or BB that are greater than 7F, because that will have them transformed into 4 bytes, which is not what you want. And so when you see this sort of restriction on your ability even to jump to memory, you then start feeling a little shaky about your ability to even write the exploit. But there's ways to get around that, as we'll see. So you have some additional iffiness because of the way the exploit is actually done. You can't use the @ symbol, you can't use slashes, and you can't, I think, use a colon, but I didn't list that here. Just because they have special meanings, they'll terminate the string, you won't get the overflow. And you kind of discover this through empirical testing. I usually just write a little script that tries all 255 characters, and when one isn't working, I kind of binary search it out. So in code red, they use this cute little %u trick, which is great. But it doesn't work for this exploit, and neither does trying to change the sort of accept languages and all the other fun things. So if you have better luck getting that to work, then you may not have to run into all these issues. But in this case, in one way, I didn't really look too hard at forcing it to accept non-Unicode data because I wanted to demonstrate that Unicode exploits are perfectly doable. So UTF-16 or Unicode or any of that stuff, for those of you who aren't brutally familiar with it, I forgot to release show Unicode, but basically, it's a very simple function in Windows, and you get OX41, or any kind of small number, and it's going to get turned into a 0041. And if you get anything above that, it's going to turn into one of these 4-byte sort of nonces, which is going to be a specific order. And interestingly, C3 is the opcode for return. So it's important to remember that if you are restricted to only having Unicode, you can still do a push of a register and then a return, which is useful for controlling execution flow. But in this case, we don't do that. It turns out we don't need it. So in some cases with this string, and the reason we don't need it, is that sometimes the Unicode function that you run through just turns anything into 0, 0, and then that thing. So sometimes you get lucky, but you shouldn't have to rely on that. So I think as you find that people are rebasing their DLLs or they're doing other things, it's often almost easier just to jump into the heap. And you can make it fairly reliable by controlling a large amount of the heap. And I mean, you can grow the heap in various ways, but the easiest way for this is just to send a lot of data. And if the heap is reasonably static, or if the process hasn't been touched, then you can pretty much be assured that you're going to be lucky enough to get into your shellcode. So the first step of gaining execution is, where are we going to return to? What are we going to set that return address to? It turns out that on the heap, at which you just do an ollie debug search. It's got a real nice search function. You just do 00170001, and pretty much the shellcode is always somewhere below that. So that's the solution that I chose to finding out, to getting control of execution in the beginning. And then you're set thinking, OK, now I have execution. Let's just write a simple decoder and be done with it. But the reality is that it's really, really hard to write a Unicode decoder. And by decoder, I mean something that will transform Unicode data into actual machine code data, those of you who are not familiar. But it's really hard to do that unless you know that a particular register points to a particular place in your shellcode. And this is pretty much it's one of the keys to trickiness of this overflow. So you then gather some information about what kinds of other features about the memory state are useful to you. In particular, what registers have writable addresses, because those registers can be used to provide a sort of no-op. And what registers point directly at your string, and where do they point? And those you then feed into basically a compiler that is going to compile a set of instructions and going to control the alignment. Because alignment is your main problem. If every instruction you have got expanded into 2 instructions, and the first byte is 0, 0, you then have to worry about what you can execute the set of instructions that is 0, 0, something, and then you can also try to execute a set of instructions that's 0, 0, something, 0, 0, and you can execute a set of instructions that's, anyway, you see it here. So you're now using these sort of primitives that you can figure out that you can use to kind of compile a little program. So that's my cool product graphic I had. But I've always felt that really what sets you apart when you're building something like this is the fact that you've invested in infrastructure. That's what the Patriot missile is, and hopefully that's what Canvas is someday. But the infrastructure that I'm giving away to you today is this make Unicode thing. It will do this job for you. All the stuff we're about to talk about, all that alignment checking, all that stuff you have now. And the way it works is that you kind of define some primitives and you build a compiler around that. So to see where the goal is, I always thought that during presentations like this, people will start getting bored unless you say, this is what we're actually doing. And what we're actually going to do is we're going to overwrite the exception handler, point to the heap. The heap, who knows where it actually is, but it's eventually going to run into your shellcode. And you're going to use that to jump into the stack, which is actually pointed to by EBX, and you know where EBX is pointing. And that's a key fact. And you know that ESI is always going to be writable, or pointing to a writable address. And then you have a small little, well, in Unicode, it's going to get, you're being able to compile a little program in Unicode means it gets huge. So you're going to have that sort of program on the stack sort of create with itself another little assembly program, which is then going to hunt the heap for another program, which is then going to actually run. So it's kind of a little tricky and fun. OK. So we need to get control of EIP at a known place in our buffer, which sounds originally very, very easy. But when you think about what your restrictions are, it becomes a little bit more difficult. So we know that EBX points to that known place. So all we really have to do is sort of modify EBX a little bit. You can increment it or decrement it to get it exactly right. Because in this case, EBX is actually pointing to a piece of your buffer that got corrupted and is munged. And you need to increment EBX to get around that. So you then need to push EBX and then return, which is the same thing as doing a call or a jump EBX, which will then execute your buffer at a known place. And that's done. OK, so that's done here. Back up here.
Yeah. So you have EBX, and you have EBX in Unicode format, right?
The question is, do we have EBX in Unicode format? Actually, EBX we don't have EBX at all. We don't control any of the registers directly except for EIP, which has been taken from the stack because of the exception handler. Well, we know for a fact, though, that EBX is pointing at our string. So you don't control it, but you know what it is. Does that help? OK. So just to show you the one little trick, auto-aligning no-ops. When you jump into a piece of code, you don't know necessarily where in the alignment you are. It could be 0026. It could be 2600. And the point is that you have to pick that it's 26, because 26, no matter what alignment you get in, will auto-align itself. Right? Does everyone see that? And it will be actually extra bonus. ESI is the writable register that you can write to automatically without crashing. And so it's just going to be writing to that register over and over as your no-op. So as we execute this, we'll have a big string of these 26s, which is, I think, question mark, in our string. And it's going to get turned into Unicode, which means it's going to be 0026, 0026, 0026. And then it's going to be jumped into at a random place. And so the little game you play, the logic game, is what can I make that 26, which the answer is 26, to survive this no matter which alignment I happen to be at. In Spark and other operating systems that do sort of aligned instructions, you don't have to worry about that sort of thing. OK, so the next trick here, and don't get too afraid of the assembly. It's not actually that complex. But the original string was just 26, 6E, 43, 6E. And that got turned into 0026, 006E, 0043, 006E. And that, when executed, says that it's going to basically be a no-op, that ESI. And then this 6E thing is going to align me so that I can execute a single byte instruction. And this maintaining this sort of, because 006E00 is a 3-byte instruction, you then get the ability to throw in just a nice 43 instead of a 0043. Because 0043 is not what I want to do. So 43 increments EBX, and then you realign again, because there's another 00 after that, so you have to do your 3-byte instruction, and then you increment EBX again. So what we have here is a mechanism for adding numbers to EBX in this bizarre little format. So it turns out that you can just use a blank C3 to return, or you can use the, in some versions of Unicode, you can actually use the, if you use FF, for example, that will actually be C300, something, 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 something. So that would return as well. So in this case, you increment EBX, you push it with 5.3, the same way you would increment it, and then you just return. And now you've done a call EBX plus some number. And that's a day of your time. OK, so this is kind of the rationale behind that. And if you didn't understand what I said, you should read this slide. OK, so now that we've jumped into our string at the stack, we know exactly where we are. We know ESI is writable. We still have some issues, some pretty hefty issues, in that we still can't write anything over 7F. without it being nonsense. And we need to somehow generate shellcode out of that, even though we know it's going to get 0, 0, 0, 0 something, 0, 0 something. So Chris Anley really did a lot of research into doing this sort of thing. He does make some, I won't call them mistakes because they're not mistakes, but he does assume that you can use OX80, which you can't in this particular case. And I wanted to be the most restrictive case as possible. So loops are great, but you don't have as much control. You don't have any instructions under this restriction that you can use to do a loop. So instead what you do is you kind of manually unwrap your loop. And you have a big, long string of instructions. And there's kind of primitives that you're going to use. You want to add numbers to memory. In this case, you want to add AH to the memory address pointed to by ECX, which is going to be basically our index pointer. As we go through the memory, we're going to increment EBX, or ECX rather. So you can see you kind of build these instructions with what you can actually do. You need to add EAX and subtract from EAX. If you can actually do it with just with one, but if you do it with two, you actually save some bytes, which is nice. And you then, of course, you want to increment ECX. You've basically built your own machine language, is what's happened. You've kind of meta machine languaged it. And at the same time, the main issue that you have to deal with, manually you could do it, but maintaining the alignment in your head is a big pain. And a lot of what the Python program does, if you look at it, is figure out what alignment would be optimal for what you're trying to do. OK, so it's also important to remember, like, what don't you know? You don't know ECX or EAX or any of those. You have to initialize those yourself somehow. And this is how. To set ECX to where your encoded egg is, you're basically going to push it and then pop it. Or actually pushing and popping. You push EBX because you know EBX points directly to you. You then realign with, that's the 006E00. And then you pop EAX, and that puts wherever you are exactly into EAX. And then you're going to add to EAX and subtract EAX so that you can actually, because you have this big long string of sort of program, and then you have a big long string of egg, and that's the encoded stuff. And so what you need to do is point something to the encoded stuff. And so that's what this little snippet does. It's adding 500 hex bytes down in the buffer from where you are to point at your encoded bytes. So transmuting between registers is actually really easy. You just do a push and a pop. And the other thing you have to do is somehow get an actual number into EAX so that you can start, so that you know what it is. And you do that just by sort of pushing a number, or just a constant, and then popping that constant back into EAX. So this is what your decoding loop looks like. And this is kind of, I noticed actually a bug in this, or a non-optimization in this that maybe I'll go back and add. But as you kind of go through, you have ECX pointing to the next byte that you want to actually write to. And instead of writing, what you're really doing is adding to it. So if it's a 0 and you add a 1 to it, it's going to be a 1, or vice versa. And the other thing you have to worry about is that they're actually rolling over. So if it's a 0 or if it's a 1 and you add an FF to it, it's going to turn into a 0. And that's kind of how you're going to get around the null issue. So you can look at this, and if you walk through it just briefly, you're going to see that you subtract from EAX a certain number once you know what EAX is. And you're kind of basically setting AH to a certain number, adding that number to what you know you already have in your encoded egg, and then repeating as necessary. So the main problem with this is that Windows shellcode, portable, good Windows shellcode, is actually pretty big. Halvar's, I'm sure, is about 10 bytes. But mine is about 560 bytes. So I mean, if I'm going to encode something, it's going to get pretty big, especially with this kind of encoder where it's really quite a hard function to fit through. So it's actually going to end up on the stack as something like 5,000 bytes, which is going to overrun the segment boundary, and you're not going to get the whole egg onto the stack. So you can't do that. You can't just say blindly, okay, I have 600 bytes of shellcode. I'm going to use this Unicode, make Unicode2.py that you provided, and it's going to go onto the stack, and I'm just going to run it, and it'll work, because it'll end up being corrupted by the end of the segment. So there are a few other issues. You're kind of restricted with the characters you can use. You can't use 40, for example. So that no matter what you do, you can't add 40 to it, because it'll end the string and not work. So there's a set of bad bytes that you maintain internal, and you say, if I'm going to add that, then I just try to add 20 and 20 instead. So it's Python, partially because Python's the best language to write in, but also because it integrates with Canvas, which is much, it's important to be able to reuse this technology for another exploit later down the line. And this is the choice made. This is basically what it does. You have it now. You can look through and see how it does this, but this is what it does. My documentation has been criticized in the past, so you may find that this kind of explanation of what's actually going on is useful. And it does work. It works reliably, except probably today when I do the demo. But other than that, it works reliably. So there's another issue that you have, and that's that size issue that you really haven't been able to conquer yet. And the way you get around that is actually by writing another little mini decoder that does this sort of nibble decoding. And you can see EBFE is just a loop jump, but it would actually get transformed via the encoder into 005E, 005B, 005F, 005E. And because some of the bytes still are bad bytes, as you say, you can kind of flip those into a nice way, with 5C being instead of 4C, which is a slash or a colon or something. So this makes the string 4 times longer, but that's better than the 10 to 12 times longer that the Unicode is doing. So this will get you around your length issue, because there's usually a reasonable size somewhere. The point is to find that place and get to it. So the place that we use is actually the heap. We already have this one magic number in the exploit. Whenever you're writing an exploit, you want to minimize the amount of magic numbers that are required to make the exploit reliable. In this case, the magic number that we're using is 17001. And we already know that number, so we just start at that number and we search through that memory until we find the nibble byte encoded egg. So that's where we're at now. We jump into the heap via the exception handler. We then have a string of no-ops that increments EBX. It returns the EBX. It then has a little Unicode decoder, which was the work of a week, but ends up only decoding a tiny little nibble decoder. It then hunts through the heap to find the nibble encoded shellcode, then re-decodes that and runs it. So conclusion there is that URL scan is not going to protect you from these sorts of things. It is possible to both use ASC.C from frac or something like this if you have a Unicode situation. I don't know of another Unicode encoder, or I would have used that. And it has one hard-coded value, which is 17001, which you jump into the heap with. And one hard-coded value is not too bad. You kind of want to remove it, and you want to try to do as much as you can to make that reliable. But in reality, I haven't found it to be too unreliable. The make Unicode 2 technology, I think, is very easily adaptable to other overflows of this type. And I think I've described earlier how I expect there to be quite a few of this type. And you can find more information on this overflow and other fun things at my website as soon as about March 12th rolls around, and I can hit up the Verizon guys to climb into the basement for a while. So Canvas is that. And that is the end of the first part of the presentation. I was going to do a demo. But are there any questions before the demo about kind of the theory?
Does it become easier or harder with UTF-8? Like if you can, if you're doing a post and you say that it's UTF-8 encoded, does that make it easier to encode the shellcode, or does that make it more difficult given the constraints of UTF-8?
So the question is it easier or harder with UTF-8? And the answer is, I don't know. I thought this was UTF-8, it turned out. And I got very confused as I traced through it, trying to figure out what encodings were getting applied when. And I think that you had all sorts of language and localization issues that were running over you. You had the service pack issue was confusing. There was 3 different versions of the string in memory. And I'd say that I tried to code for the worst possible case so that it would be easy no matter what. And hopefully that will turn out to be the case. That was a good question. Any other questions?
I'm still kind of confused on how to get control of execution. I mean, here you're saying that you push EAX and you return, right?
OK. So the question is, how do you get control of execution? And you get control of execution because you've written such a long string onto the stack that you've overflowed the segment boundary. The stack has ended, and now it's going to complain, and it's going to cause an exception. And when it causes that exception, it's going to go to the SE handler, which is you've overwritten because that's on the stack, which was fantastic. And
That's Unicode. That's a Unicode value.
so then I control EIP.
Unicode value.
It's a Unicode value, yes. It's completely Unicode. You have no way of getting control of the other 2 bytes.
So how can you jump? You can jump to only a limited number of
Exactly. You can only jump to a limited number of places, and the place that I chose was 0017, 0001, because that's on the heap where there happened to be a big chunk of my string.
Right. But there's a range. I mean, you cannot go over
Right, you can't go 0080, for example. You couldn't do that.
or more than or 6x.
Right. Well, I mean, you can literally only go 0041, 0041, or 0001, 0001. The highest number you can do is 007F, 007F.
So yeah, you have to rely on the fact that you're going to have a bullet heap below that.
Yeah, this does rely on the fact. OK, this technique does rely on the fact that you can jump somewhere where your string exists.
That's part of it.
Right. Well, I mean, the other case is that you can sometimes find there are text pages or code pages which have things that are very useful, like a call ESI or a call. But it turned out that it was actually more reliable to do this.
Now, how different is your method for patching and decoding to the Venetian exploit?
How different is this
To the Venetian.
to the Venetian exploit? And I think it's quite different, because the Venetian exploit, I think, it's a slightly different function. They don't have these zeros inserted,
They
which
use
is
the 80, right?
yeah. They have a better function to work with in a way. That's actually really good work. I've used that, but this is, I think, specific for this Windows subset of problems that I think are going to come up more and more commonly. And but it's a very similar kind of problem.
You are walking through your buffer while patching, right?
Yes, as well. I'm walking through my buffer as I patch it. Any other questions? Any hecklers? All right, so the demo is going to be pretty quick. This is why I say this. Well, we can drag it out when it stops working and I try to debug it. All right, so this is Canvas, just so you know what you're seeing. This is my product. It is all Python. All right, so what I just did is I set up this little listener. So that's where the shellcode is going to call back and connect to this, and that's what's going to provide all my functionality. And I'm not going to go into how the listener works, because that's an entirely different talk. But the other thing you have to know is that, well, there's really not much else you have to know. Come to think of it. So AE security service is running. It's just this is the default install. I haven't done anything patch-wise or anything else. And you can run it over SSL, as Riley mentioned. IDSs don't look at SSL. It's going to hit enter. It's going to freeze for a little while my GUI tries to figure out whether or not it worked. So this GUI is basically doing all that stuff that we just talked about. Huh, I knew it. It's going to, sweet. All right. Now that's luck. But all that stuff we just talked about, because it generates all the shellcode on the fly, and then it wraps it in these layers. And one of the layers that it wraps it in the end is the layer that is going to put it into the Unicode format that it needs to be in. So if you look at the file that I gave out today on the website, you'll see, and it's GPL, so you can feel free to modify it and redistribute it under those terms. You'll see that it actually is, there's a little thing called make MCSS shellcode. And you can, I'm sure, use your own shellcode if you have good Windows shellcode. And you should be able to write this exploit in a couple days, if that. And I guess you probably don't believe me that this exploit actually worked. This little thing is that's the actual connection back. And you go down a little syscall redirection toolkit. You can pop this up. You can do things like, yay, we can do whatever you want. You're running a system, right? So you can upload, download files. I find all that very entertaining. But that's it. That's the process of writing an exploit that has difficulties. That's not just a Stack Overflow that you've read about in every book on the planet. This is actually for fun and profit. So more profit if you buy Canvas. But are there any questions about that? Does anyone want to click it? It's fun. If you're not enjoying it, you're not going to do it. So that's that, and I hope you guys had fun and learned something.